Our next presenter, again, is no stranger. We have an all-star lineup here today. No stranger to the Virtual Water Expo audience and the Water Online universe as a whole. He is none other than Stephen Horne with Kaeser Compressors. He is going to be discussing and exploring how to maximize wastewater blower station performance, evaluating how the selection of blowers with specific efficiency envelopes impacts the process across the full system operation range. He will also be discussing isentropic efficiency and how it differs by technology type and how these blower types compare in the installation environment. Stephen, take us away.
Okay, thank you, Travis, for the introduction. Let's go ahead and get started with our topic here, which is station performance planning for your blower station. Let's do a quick overview of the objectives, what we hope to get out of this. First and foremost, we're going to talk about blower control modes. Then we'll define efficiency, which will be an important part of our discussion for evaluating blower stations and doing an evaluation. Then we will define and look at what an N+1 blower evaluation is. And then we'll take a look at some of the station comparisons across different technology types, which I know is something that everybody is always interested in for their blower selection. Okay, let's get started with blower control modes. So I have 4 control modes here I'm going to discuss. I think these are the most basic ones that most people should have some reasonable knowledge with, but we'll go ahead and define them. And knowing your control mode, I think, is a critical part of understanding how you control your blower station. Until you know how you're going to control your blowers and what the blower, what this will look like, what you're going to get out of your blower, controlling your station is more difficult. So I think it's important to understand what control mode you're going to use with your blower whenever planning your station and then ultimately controlling your station. So the first one, flow control. This is historically most common with your dynamic blowers. So this would be like your multi-stages, your geared turbos, and of course nowadays your high-speed turbo. Historically, this has always been an ACFM, your inlet flow control method. But in this day and age where we have more and more sensors being put on equipment, these controllers now have the ability to calculate what the SCFM is. And of course, you know, most of our wastewater plants are controlled by pounds of air or SCFM. So with the temperature probes, the controllers are now able to alter the machine based upon SCFM. And I said before, historically, this is a dynamic control mode, but as I said, we're throwing sensors on machines, and now you can get complete blower packages, which are positive displacement. Those are your rotor lobe and rotary screw, which can also be controlled based upon CFM. So flow control is an old method, but has been evolving and is currently a very valuable methodology that can be used to control your blower station. The next one is pressure control. It's been around as long as flow control. Here, what we're doing is we're altering our machine speed or output to maintain a constant discharge pressure. So if you had an old multi-stage machine, you might have a valve at the basin that you throttle back, and then this throttles your multi-stage machine. If you had a positive displacement machine and you throttled back, you would start building pressure. It wouldn't automatically modulate itself, and it could blow a relief valve, kill the blower, or pop a relief valve. Or if you had something like a weighted loaded relief valve, it would vent off that air. But in positive displacement, this has always been a way to increase your pressure, which then increases your power consumption. So not the best. Modern day, we have VFDs on our machines, whether it be a multi-stage or a positive displacement with a transducer. And now you can have your machine follow a pressure set point based upon your system. And as I mentioned, this is very reactive. For the most part, safe with positive displacements unless you're slamming it shut on a fixed speed machine where you can overload it. And also mostly safe on dynamics, but you have to be careful on dynamic machines because if you start choking it back too much without any provisions, you can hit surge point on your multi-stage or dynamic or high-speed turbo machine. Next one is speed control. Ever since we've had VFD, speed control has been really the favorite one. So if you need more air, you increase the speed. You need less air, you decrease the speed based upon your hertz on your motor. This has been mostly safe with positive displacement and multi-stages and dynamic machines, but and particularly with turbo blowers, with their speeds that they're running at, you do have to be modestly concerned about where that surge point is and where you're operating. Many times your dynamic turbo machines, you probably want to use flow control. And the last one is an oldie but goodie. You need air, you turn it off. You don't need air. You need the air, you turn it on. You don't need air, you turn it off. And if you had demand where it changed seasonally, particularly on positive displacement machines, you could change pulleys by season to really drastically change your flow rates if need be. So those are the basic control modes. So understanding those is kind of the foundation of what we're talking about with controlling your station. But the next one is efficiency. And when I say efficiency, I think everybody thinks about something different. We have efficiencies on motors. That tells us how much power efficiently the motor is consuming power. We have volumetric efficiency on the blower block. That tells you relatively how efficient the blower is to what it could be. But what I am talking about is isentropic efficiency. So isentropic efficiency is a comparison to how much power per flow you're producing your machine compared to what the ideal process is. So this is a way to determine how truly efficient the package or the equipment that I'm using is, and we will use that in our evaluation. So whenever building a blower station, we have a grouping of blowers in the room, and that could be one blower, but typically it's two blowers or more. So we say N plus one. So if it's just a two blower station, one blower, one running, one backup. So that's a 1 plus 1. If we have two blowers running, one is a backup, then it's 2 plus 1, and so on and so forth. We can keep on adding blowers for this. So the more blowers you have in a system, the more fine control that you might have for turning different flow rates and achieving different efficiencies. But the difficulty with the add blowers is that it takes up more space in the room more times, and also how you control them, knowing where you are and how you're controlling them. So it's important that you have more blowers that you have a good control system for that. But this gives you a nice steady efficiency, but again, can be a bit more complex. The next thing you need to think about is investment cost. Does more blowers cost me more, or do fewer blowers cost more? And this is kind of depending upon the size of machines that we're talking about. If you get into really high flow rates and you have a 2 plus 1 system, you have two big blowers and you have one big blower just sitting there doing nothing, that can be rather expensive because those machines can be costly. And so splitting those up into smaller machines, you're utilizing more units. And then that backup blower, which is just sitting there, often doesn't cost as much as if buying a 2 plus 1 station. So what we're going to do here is we're going to take a look at a way to evaluate that and then help you make the better choice for making that selection. So let's have a look here at all screw blowers. I'm going to look at a 2 plus 1, a 3 plus 1, a 4 plus 1. You can see the motor sizes I selected. There's our control range, and we're at sea level and 8 psi. So really no real interesting thing about that other than we're using these values for our evaluation. So here are the three stations. We have our 2 plus 1, the top left, our 3 plus 1, and the 4 plus 1, and we have our efficiency curves for the system. So what this does is on the top left, we have 2.1. So we have two machines running. So in the beginning, we have two machines. Then at some point, we blend the second machine. So one machine to two machines. And then, so each time you see that wave going up and down is where we are blending in another machine into the system. So it looks kind of confusing and wavy. But this next chart, we can plot them on top of one another, and we can see how the different combination of machines impacts our efficiency. So the big machines, you can see the 2 plus 1, it's the variations are, the waves are kind of big and rolling. There's not much ups and downs. Whereas more machines we add, the more up and down we get, but the curve kind of flattens out. We have less variation, as mentioned before. So it gives us more opportunity to optimize our efficiency. So let's take a look at this evaluation. Let's assume, when we're talking like 1200 to 6000 CFM, let's assume we spend most of our time running right in the middle of that, so about 3000 CFM. And here we can see at $7 per kilowatt hour, how much it would cost to run those machines, the station. So here it's pretty much the same. Not a lot to be talked about, but again, we need to consider how we're going to control our units and what the investment costs and installation costs. But let's have a look if we move that down to the left. So we're going to run on the lower end of the flow scale. Now we start seeing a difference in how much energy is being consumed. So, okay, so now the 2+1 looks pretty good. So probably running one machine at a pretty efficiency point, but the 4+1 didn't change much at all. Remember, I had a pretty flat curve, so really no gains or losses for variation. But let's move it to the right. So if we move it to the right, we can start seeing that we're start hitting different efficiency points in that station curve. And now you can see the 4+1 again hasn't changed much, but now is the most efficient one. So what does this mean? Well, this means we need to evaluate our efficiency curves and where we're going to think we're going to be running this station. So if it's a new station where we're not going to be using the full demand, we're going to be running on the lower end. If it's an established system or more industrial system where it's more predictable where it's going to run, then you can kind of pick and choose where on this efficiency curve that you're going to be running and what the combination of machines you think would be most efficient. And again, as you add machines, that control comes a bit more complicated. So you need to have a good understanding of the blower control method and how you're going to cycle these machines on, and when you're going to blend in from one machine to two machines to three machines, etc. So that's kind of a quick evaluation of how you can take these efficiency curves and stack them up for a single technology. And so I promised to take a look here across technologies. So let's take a look at a screw, a turbo, and a lobe. Same design parameters. And here are our efficiency curves once again. So I think the top left is screw, top right is turbo, and bottom is the lobe. Let's stack them on top of one another. You can see here that the screw, there's a bit of a surprise to see, it is the most efficient. It's pretty close to 80%. Our turbo blower is not too shabby. It's over 70%. And I suppose if I picked a different turbo, I could probably get closer to 80% out of the turbo, or maybe a little bit better. But again, that window for a turbo runs at its high peak efficiency point is more narrow. But nevertheless, and then down at the bottom, we have the lobe blower. Of course, these have been around for a long time, but you can see that efficiency suffers below 60%. So those older technologies like your lobe and your multi-stages are going to be similar to that 60% line, and the new technologies, turbos and screws, will be higher, between 70 and 80%. So we'll do a same evaluation right in the middle. Here we can see, no surprise, we saw the efficiency of the screw was better in this condition, how it is more efficient. And of course, we can see how the old technology is suffering. But again, we need to know what size is the room, how we're going to fit these machines in there, and also what that machine cost looks like. And then again, we can just shift the curve over to the right and to the left. We can see how the two technologies get tighter together when the efficiencies are closer to one another, and how they vary apart as the efficiency points move. And of course, again, we see how the old technology continues to suffer in these scenarios. All right, so let's do, again, we're back here to how these things are laying over top of one another. We can see, depending upon the flow range we're operating in, how those efficiency points converge and go apart from one another. And again, we can see how the new technologies, again, offer us a lot more benefit. So a quick conclusion. Blowers are available in a variety of control modes, and we saw how important those control modes can be when we're looking at the entire control range of the station. So how we control the blowers, how we're going to turn them on and off, and how we're going to blend them in as we add machines and take machines away. And of course, knowing your technology will help you decide which control method is the best, and also helps you know the selection for where its peak efficiency point is. So knowing where you're going to be running your station and where those blowers are going to be running allows you to select the piece of equipment that is the most efficient for your application. And then, of course, the newer technologies provide you nice savings across the entire control range. But then again, what does your budget look like? How much you're paying for electricity? All these things can factor into your decision making about which one that you need. And again, the more blowers you add, the less variations you can have in efficiency. But again, the more complex your blending of machines become. So these are all different factors you want to take into your consideration. And again, the more complete your evaluation, the better decision you're going to make for your process in the end. So I hope that this little summary of control modes and blower station efficiency helps you understand how these new technologies and blowers can be selected for your process and systems. And again, thank you for your time. And of course, if you have any more questions, I hope that you reach out to us. But thank you.
Thank you, Stephen. Wonderful presentation. As always, we appreciate the data, the presentation, and all of the information you shared with us today.